Welcome everyone. This is Flow, which is as the name suggests, is a seminar series on federated learning, broadly construed. As some of you may know, we host speakers on a wide range of topics related to the area, obviously machine learning, but also distributed optimization, privacy, and crypto. So if you have any suggestions for speakers, feel free to send them to us. Two quick admin things before we start. If you have questions during the talk, please write them into the chat or raise your hand, and then we'll keep track of this and we will unmute you when sort of a good time for an interruption comes. Also, this talk is being recorded, which is always good to know. That being said, it's really my great pleasure to introduce Hamid Hassani, who is currently an assistant professor of electrical and systems engineering at the University of Pennsylvania. He's been affiliated with the Simons Institute at UC Berkeley and ETH Zurich, and got his PhD at EPFL. Introducing Hamid is a bit difficult because he has so many awards. So I will actually have to cut this part short, I believe, but I will say that I think he got pretty much all of the awards which a kind of young rising star in the area could have gotten. I will just mention the Intel Rising Star Award, which he got in 2020, and also the NSF Career Award. So I'll stop here, and I'm really looking forward to his talk. You have the floor.
All right. Thank you very much, Dan. Hello, everyone. I'd like to thank you all for attending the talk, and also special thanks to the organizers for inviting me. So the talk will be about systems heterogeneity in federated learning. And I'd like to begin with saying a few words about what systems heterogeneity means and how we mathematically can think about it. So I guess, as you all know, one of the main goals in federated learning is to train or learn a shared model across a large and diverse set of clients that use, let's say, different devices. These devices could include, for example, mobile phones or tablets, or it could be devices in some mobile or moving cars, or more generally, it could be devices in some autonomous vehicles, which are, let's say, monitoring some area, like gathering data and sending it to a server. Or again, as another example, the device could be just your personal computer, which is connected in a wireline fashion to a network. And finally, we can also consider a broad set of smart devices, for example, smart watches, which are more limited in terms of their computational power as well as connectivity. So the main point in federated learning is to involve all such devices and clients in the learning procedure in order to be able to use the data that's available locally at these devices. And by using more data and involving all such devices, we'll be able to learn more accurate models. But the main challenge here is that such devices may have different storage, computation, and communication capabilities. And this is due to the variability in these devices in terms of hardware, network connectivity, battery power, and several other factors. So this difference in computation time and computation capability can be translated into the following simple but yet rigorous model. So we assume that we have a typical federated learning scenario, a server which cooperates with a set of clients, end clients here. And we assume also that each client is associated with a time Ti, which is the amount of time the client needs in order to do local processing. And of course, since we are assuming that clients have different computational capabilities, these TIs could vary among the clients. We have some fast clients that have a small t, and we also have some slow clients that have a very large t. And what's important is that typically in a federated learning scenario that involves a large number of clients, we would see a notable fraction of slow clients for which these processing time could be large. And in a typical federated learning scenario, if we want to wait for all the clients in each round, and due to these slow or struggling clients, we might have to wait a considerable time, right? So the max of TIs could be very large, in fact, in practice. So one naive way to basically resolve this issue of straggling clients would be just to ignore those slow clients and just go according to the fastest clients. Okay, that's just the most naive way to basically resolve this issue of heterogeneity. So basically, by just going according to the fast clients, we're just involving those fast clients in our training procedure. What happens is that we go according to the minimum of the TI, so we are very fast. However, since we are not using the data of those slow clients, we would lose a price, we would lose in terms of the total accuracy of the model that we will learn, right? So in other words, slow clients are important for us because their data is valuable. And we would use their data in order to gain models with better accuracy. So there seems to be an interesting interplay between speed and accuracy here. On the one hand, we don't want to wait for slow clients all the time. And on the other hand, the data of those slow clients would be very important for us. And working at the best operational point within this interplay is something that we're going to design algorithms for. So that's an intuitive picture behind systems heterogeneity. Let me dig a bit more into this problem and introduce some of the notions that are also used in a typical federated learning scenario. So in a typical federated learning scenario, each client is also associated with a client-specific objective function that measures the performance of the model that we are trying to learn on client's local data. So typically Fi would be written as an empirical sum over all the training data points in the client's data set. And the sum is over the loss function evaluated at the model X on the data points, training data points inside client's data set. And more generally, Fi could be just an expectation over the loss on the client's distribution. And something that we also assume throughout the talk is objective heterogeneity. This means that these client-specific objective functions vary across the clients. Or in other words, the distribution, the generating distribution of the data for the clients could be quite different. Okay, so FIs could have different structures as well as different landscapes. Now, the goal in such a federated learning setup would be to minimize the sum of these client-specific objectives, sum of FIs. So the server and the clients would cooperate with each other in a federated manner in order to find a solution to this global objective function that you see, or the global minimization problem that you see on the top right. Essentially, they want to minimize this function f, which from now on we call the global objective function. And f is given as a sum over FIs. Now, a typical federated learning algorithm would proceed as follows. It would proceed in rounds or in communication rounds. In each round, the server first aggregates the updates or the information that it has received from the clients, and it aggregates them into a model that it computes, a shared model, x bar of t, as you see on the top. X bar would be the iterate that will be updated gradually within our algorithm, and in the end, it would converge to a good solution to our objective, to our global objective function that you see on the right. Now, once the server computes X bar, it will broadcast it to all the clients, and each client basically does a few rounds of local updates on this model that's been sent by the server. Okay, so let's say H rounds of local updates. You can think of these local updates as gradient updates. That's the simplest form of a local update, just to gradient descent using the client's local objective function. You do H rounds of gradient descent, for example. There are, of course, a variety of other federated learning algorithms by now, which do different types of local updates. But what's important is that you do H iterations locally on the model that was sent from the server. Once these H local updates are done, the final model, the updated model at client I, will be sent back to the server, along with some other information that might be relevant to the server and other users based on the algorithm that we are using. Okay, so once these updated models are sent to the server would process these models. For example, in the simplest manner, the server could just take the average of all the sent models, and that would be the X bar T plus 1, the shared model for the next round to be processed. And this procedure continues in several rounds until we reach to a good solution of this global optimization problem. Now, this is typically how a federated learning algorithm would work. Now, and the picture that we should have in mind, or the conventional picture that we have in mind, is that in each round, each client is performing, let's say, a number of local steps, let's say H local steps. But when we are talking about systems heterogeneity, this picture is not exact, meaning that the time that it takes for each client to do these H local updates might be different. Just a minute, there is a problem. I don't know why my keynote is not. Just a moment, sorry. There is a. All right, so now it seems that things are working. All right, sorry for the. When clients have different computation times, have different speeds, some of the clients are faster in terms of computing the H local updates. Some of the clients are slower. And in fact, maybe some clients are much slower, meaning that it takes them a lot of time to do these H local rounds. So we reach to this, again, to this trade-off or interplay between speed and accuracy that I was mentioning beforehand. Of course, in each round, we don't want to wait according to the slow clients, because that would considerably increase the waiting time and the latency of our algorithm. But at the same time, the data of those slow clients are valuable. So we would have to involve those slow clients in our training procedure from time to time. Now, in order to basically, I'm sorry, there is a, I don't know, there is a problem with my keynote, or yeah, just a moment, it's not working properly. All right, just a moment. I would start to. All right. So in order to solve this systems heterogeneity problem, there are so far two approaches, namely the deadline-based approach and the adaptive selection approach. Now, the deadline-based approach is actually a simple idea. In each round, we would allocate a fixed computation time to all the clients, like a deadline. And once this deadline is reached, we would ask all the clients to send us their update, to the server, no matter how many computation or how many local rounds they have done. Okay? In other words, in the deadline-based approach, you assume a fixed computation time for each round, which is fixed for all the clients. Within this computation time, the clients could do as many rounds as they could, right? More precisely, client I, within this fixed computation time, could do tau I local steps. And tau I is obviously related to the ratio between the allowed computation time divided by the time needed for that client to do one local step. So in this sense, clients that are faster can do more local updates. They have a larger tau I, and clients that are slower can do less local updates. They have a smaller tau I. That's the deadline-based approach. So you give a fixed deadline to all the clients. Once the deadline is reached, they basically send up whatever update they have done, right? And this would translate into having client-specific number of local steps, which we denote by tau I. Now, the adaptive selection procedure is something different. In each round, we would choose a subset of the clients. The choice of the clients, the selection procedure, is an adaptive procedure that's done according to the algorithm that we have. And what's important here is that once these selected clients are selected, at each round, we would wait for all those clients to perform H local steps. And then once those selected clients are finished, they would send to the server basically their updates. So in other words, in the adaptive selection approach, the time in each round is variable, right? So the total wait time in each round would be the slowest, it would be specified according to the slowest client in the selected set. Okay, so more, if I want to explain these in a more mathematical manner, so at each round, we would select a subset ST of clients. These clients are the ones that we have selected to participate in the training and learning procedure. And we would wait for all those clients to finish their job, right? So the time that it takes for each round to finish would be basically the maximum TI over all those clients that are selected. So these are, as I said, so far, two main approaches to systems heterogeneity. Now, in this talk, we will consider both approaches. The first part of the talk will be about the deadline-based approach. We will introduce a method, which is called FedLin. FedLin is an efficient algorithm which works in the presence of both objective and systems heterogeneity. And as we will see, FedLin is quite a powerful algorithm in the sense that it achieves the convergence rates of centralized optimization. So the focus of the first part would be mostly on the optimization aspects of federated learning in the presence of objective and systems heterogeneity. In the second part, we will consider the adaptive selection approach. We will introduce a different algorithm, which is called FLAMP. And this FLAMP is an adaptive selection approach, which basically uses this interplay that I've mentioned between statistical accuracy and systems heterogeneity, and basically finds the best operational points with respect to this interplay. We will also, towards the end of the talk, hopefully if we have time, we will talk about theoretical guarantees for FLAMP, as well as experimental results showing superiority of FLAMP with respect to the other baselines. All right, so let me proceed with the first part of the talk, which is on deadline-based approaches. This is a joint work with Aritra Mitra, who is a postdoc at Penn, and Rayana Jafar, who is a PhD student. Aritra and Rayana are really the brains behind this work, and they are jointly advised by Professor George Papas and I. And the paper is also available online. All right, so in the deadline-based approach, we have a clean optimization problem actually to solve. And the optimization problem is the following. So remember, each client was associated with its objective function fi. We are assuming that fi's could be arbitrarily different. This is objective heterogeneity. And further, each client does tau I local steps. Think of it as tau I gradient steps that it can do, right? And within this scenario, we would like to design algorithms that minimize this global objective function f that you see on the top right. And remember, tau i's are different across the clients, and that would be systems heterogeneity. Now, this is our optimization problem. Let's start with the simplest, but perhaps the most interesting setting for this optimization problem. And this is when fi's are assumed to be strongly convex and smooth, right? In this case, the global objective function f is also strongly convex and smooth. It has a unique global minimizer, x star. And we know that in the centralized setting, where if we just do, let's say, gradient descent on the objective function f, nothing federated here, just do gradient descent on f, we know that we can converge exponentially fast to the global minimizer x star because of a strong convexity and smoothness. And this is typically also called as linear convergence. Okay, so in centralized, we have very fast convergence in this setting. Question is, can we also achieve linear convergence in the federated setting? And again, a natural follow-up question would be, what's the behavior of the state-of-the-art or previous methods? As I will describe now, previous methods would suffer from something that we call speed accuracy conflict. And because of this conflict, we will explain that previous methods are unable in general to reach linear convergence in this setting. And then we will introduce our algorithm. Okay, so here, just to explain this speed accuracy conflict, I'm going to focus on one recent method, which is a very interesting and elegant method called FedNova, which was proposed by Wang et al. In NeurIPS 2020. And FedNova considers, again, both objective and systems heterogeneity. And one of the main observations in this FedNova work is that in the presence of systems heterogeneity, the previous algorithms, such as Fed average or other algorithms, would even reach consensus or converge to incorrect points. So not only they may be possibly slow, but also they might even converge to a point which is different from the global optimizer of the problem, which was X star. Now, in order to basically alleviate this effect of this objective inconsistency that they observe, they propose a method, a federated learning method, which basically proceeds in the following manner. So in terms of local rounds, if you see at the first line here, in terms of local rounds, we just do tau I gradient updates using the local objective functions fi for each client. Now at the server, FedNova does something different. Now this is the update, and second line would be the update that's done on the server. Intuitively, this update is a weighted aggregation of the models that are sent by the clients to the server. Okay, I'm not going to go into details of this update rule, but we should think about this as a weighted aggregation of the models sent by the users, and the weights are proportional to the client-specific local steps, tau i's. Okay, so it's an adaptive method really for the deadline-based approach. And so that's the FedNova algorithm. The question is whether or not it has linear convergence. The answer is not in general. And as I will explain in the next slide, as we will see, FedNova, even though FedNova is trying to basically remove this objective inconsistency that was due to this challenge of systems heterogeneity, it can be shown that FedNova itself has some other inconsistencies in its objective. In other words, FedNova minimizes a different or a surrogate objective, which is different from the original objective function that we have to minimize when we have a non-zero learning rate. Okay, let me elaborate more on this. So consider a simple example where the functions fi's are quadratic functions, okay, as you see here at the top. So each ai's could be simple matrices, and fi's are just quadratic functions, strongly convex functions, basically. Now, what we can show is that in this example, FedNova minimizes an objective, f tilde, which is sum of f tilde i's, and f tilde i's are distorted versions of fi's. Okay, so here, if you look, the matrix qi's are the distortion matrices, and well, ideally you want to have qi to be the identity matrix, but qi would be identity only if eta, the learning rate, would be 0. Okay, so that's the problem. If the learning rate is non-zero or is not vanishing by time, then FedNova also ends up converging to a incorrect point. So it doesn't converge to X star. And through simulations on these simple objective functions, we will actually see that the bit rates of FedNova, if you look at the dash curves here in this plot, the dash curves correspond to FedNova. If you see the distance between the iterates of FedNova and the global optimizer of the problem would basically converge to a fixed and non-zero number, okay, the dash curves. And here the solid curves, the lines basically correspond to the algorithm, our algorithm that I propose, and you see these algorithms have exponential convergence, while FedNova basically converges to an incorrect point. So in other words, for FedNova, in order to converge to the right point, the step size or the learning rate should be diminishing, should basically vanish as time goes on. Otherwise, if we use a fixed step size, FedNova would converge to the wrong point. And this is precisely the speed accuracy conflict that I was talking about. In order to, on the one hand, if you want to have fast convergence, linear convergence, you have to choose the learning rate to be a constant, right? To be non-zero, and it shouldn't vanish with time. But once you choose learning rate in that manner, you would converge to the wrong point. So you would lose in terms of the accuracy. and vice versa, right? If you want to be accurate, you have to choose the learning area to be diminishing, and in this sense, you would basically lose linear convergence. And simply aggregating normalized gradient as done by FedNova basically doesn't resolve this conflict. And you can show that the same type of speed accuracy conflict also holds for Fed average as well as the FedProx algorithm, which are two celebrated algorithms for federated learning. Both of them also suffer from this conflict. So they basically converge to the incorrect point. So long story short, so far there is no existing FL algorithms that guarantees linear convergence to the global optimum of the problem X star under both objective and system heterogeneity. And now is a good time to basically explain what we propose, the algorithm FedLin. Here I'm explaining it for a strongly convex function, but you can essentially show, and as we will do, that it basically succeeds to recover all the centralized rates for other structures such as convex, non-convex, and so on. Okay, so hold on to that. We will go back to it at the end of the first part. Okay, so what is FedLin all about? So remember, we have two challenges here: objective heterogeneity and systems heterogeneity. FedLin is based on two main ideas, which respectively try to resolve or address each of these challenges. Let's first focus on objective heterogeneity. So objective heterogeneity is when the functions fi's are different. Remember that. Now let's focus on the typical local updates that many federated learning algorithms do, including FedNova. So the typical local update would be that you do tau I local rounds at client I at a specific round. And these local rounds are gradient descent updates using the local objective function of client I, which is fi. Okay, so that's a very typical, and that's what Fed average uses, that's what FedNova uses, just do gradient descent according to my local function fi. Now, of course, once you are doing gradient descent, and for example, when fi's are strongly convex functions, you would converge very fastly, actually exponentially, to the minimizer of the local objective functions fi, right? This is just gradient descent, right? Gradient descent converges fast to the minimizer of fi's. But when we have objective heterogeneity, fi, the local function fi, might be quite different than the global function f that we want to minimize, right? These two functions may be very, very different from each other. And in particular, their minimizers, the minimizer of fi could be very different from the global minimizer of the problem x star. So in other words, we are somehow suffering from this client drift phenomenon, the so-called client drift phenomenon that has been also explained in prior works, which by just doing gradient descent using fi, we might actually get away and away from the actual minimizer of the problem, which is x star. So this is a problem here, and this is a general problem for local update rules that are only based on fi's. Okay, so let's see how we can resolve this issue. Well, and let's first think about what would be an ideal way of updating. Well, ideally, we want to minimize this global objective function f, right? So what would be really good would be to go according to the gradient of the global objective function f instead of fi's, right? So if client I could do gradient descent with the actual objective function f, then somehow the problem of objective heterogeneity would be resolved, right? Because I'm basically going towards the actual minimizer of the problem. So in other words, ideally, we want to have updates like this, which is according to the gradient of the global objective function. But this is not possible in a federated setting, because in a federated setting, client I only has access to its own local data or its own local objective function fi. Now, a simple idea here to basically resolve this issue would be to exploit memory. Okay, so the idea would be the following. So we remember and use the gradients of the global objective function that have been computed by the server in previous rounds. Let me elaborate more on this. So at round T, just before round T, the server, using the updates coming from the clients, can actually compute the gradient of this global objective function f exactly at the point x bar t, right? This is x bar t, remember, it was the shared model that the server computes. And this is easy for the server to compute. So we have actually a global information, the gradient of f at x bar of t, at the server in round T. The server could actually broadcast this information to all the clients. So clients have access to this information. The idea would be, the idea of exploiting memory would be to use this gradient of the global objective function as a guiding direction in our local steps for each client at round T. Okay, and the final update rule is given as follows. Let me explain what this update rule is all about. Now, of course, we want to use the gradient of the global objective function, but at client I, we can actually update this global gradient according to our iterates. This is because at client number I, we have access to fi. So actually, we can update at least the part inside the gradient of the global objective that corresponds to fi, right? And this update rule that you see at the bottom is exactly doing this. So at else local round, we would basically subtract from the global objective function, from the gradient of the global objective function, gradient of f at x bar t, we would subtract the part which corresponds to fi, the slate or the old part, the gradient of fi at x bar of t. And instead of it, we would add a fresh gradient, which is the gradient according to fi on the current iterate of the algorithm, of the local algorithm that we are running. That would give us the following update rule. So we use this the gradient of the global objective function, but we only update a part of it which corresponds to the local objective function fi. Okay, and that's the update rule for client number I. Okay, so using this update rule and by exploiting memory, we are somehow taking care of objective heterogeneity to some extent. Now let's focus on the other challenge in our problem, which was systems heterogeneity. Now, in order to address systems heterogeneity, let's start with a simplest scenario. Let's assume that actually we don't have systems heterogeneity, and assume that all the clients can do exactly H local rounds. Okay, let's first consider this setting. In this setting, our analysis reveals that in order to be able to obtain linear convergence to X star, it is absolutely necessary to choose the learning rate for each client to be inversely proportional to 1 over h, where h was the total number of local updates. Okay, so that's necessary. There's no way around it using this update rules that I mentioned. And this is intuitively because of the fact that the drift term of the local updates scales linearly with h. And in order to basically control this drift, we need to basically rescale the learning rate by h. Okay, just to control that, just to basically prevent these local variables not to get too far from the actual average. Now, okay, going back to our system heterogeneous setting, each client can do tau I local updates, and tau I's vary across the different clients. Now, exactly the same thing would happen in terms of the drifts. Client I, the drift of client I, by doing tau I local updates, would still scale linearly with tau I, the number of local updates that this client is doing. So a natural idea here, according to what I explained in the previous slide, would be to rescale the client-specific learning rates by tau I. In other words, in order to address the challenge of systems heterogeneity, we would use client-specific learning rates in the update rule that I mentioned 2 slides back. And the client-specific learning rates are proportional to 1 over tau I, where tau I is the number of local updates for each client. Now, this way of choosing these learning rates might seem very conservative to some of you. it might even go against conventional wisdom, right? Because somehow if a client is a fast client, meaning that it can do many local rounds, many local updates in each round, it has a large tau I, we are somehow penalizing that client. We are somehow controlling that client more by assigning to it a smaller learning rate. So that's somehow very conservative, right? But actually, because of this heterogeneity in the objectives, this is necessary, right? Let me explain why. Let's assume that you have a very fast client, very, very fast one. It has a very large tau I, but the objective function of that client, fi, is very different from the other, is very different from the global objective function. So by doing gradient steps, according to fi, we are having a very large drift. And the client is fast, so the drift would be huge, right? If you do many, many local rounds, the drift would be very bad. So we have to control this drift. And to do that, we have to rescale the learning rate of that client. So this is conservative, but somehow necessary. And we will see that using these two ideas, namely the update rule that I mentioned and the client-specific learning rates, we can actually achieve linear convergence rate, and we can match the centralized rates in other settings too. Okay, so the final algorithm would be the following. So remember, I'm explaining two ideas: client-specific update rules, eta i's for each client, and also the update rule that I mentioned in terms of exploiting memory. Here, we also employ a gradient sparsification compression, because you know that one of the main ideas in federated learning is to use compression, because we want to reduce the communication load in exchanging messages between the client and the servers. So typically, compression would be applied on the top of these algorithms that I mentioned. So here, this vector GT that you see in the update would be an inexact version of the gradient of the function, and this is because of compression. So this is a compressed version of the gradient, but the update rule is exactly as I mentioned in the previous slides. So this is the final algorithm. And before explaining the main theoretical results, let me also mention that this final algorithms has some similarities in terms of the ideas with some prior work, and also has some key differences. So similar to FedNova, we are using client-specific learning rates, but the key difference with FedNova, which, as I mentioned, is a state-of-the-art method for systems and objective heterogeneity, the key difference is that there are two differences actually with FedNova. The first difference is that we are using client-specific learning rates for the update rules. FedNova doesn't do that. And also our update rules are different. We are exploiting this idea of memory, which FedNova doesn't do that. So this idea of using memory is closely related to the idea of gradient tracking in distributed optimization. It's a well-known idea and used quite frequently in distributed optimization. And also the idea of exploiting memory has also been used in various reduction techniques in stochastic optimization. Algorithms like SAG, Saga, SVRG, and more recently Scaffold in the context of federated learning use this idea of gradient tracking. Now, there is another algorithm called FedSplit, which also aims at achieving fast rates. It's proposed by Pathak and Wainwright in NeurIPS 2020. So FedSplit is based on some operating splitting techniques, and basically in each round it does something novel. It solves a proximal optimization problem instead of doing like gradient local updates that we mentioned. Now, what can be shown is that FedSplit for strongly convex and smooth functions converges also linearly, but to a neighborhood of the global objective function. And this neighborhood doesn't really vanish. It's always there. So so FedSplit cannot be assumed to have linear convergence because of this error flow. And in the paper, we also have a thorough discussion on connection to other works in this area. I would just refer to the paper due to time constraints. All right, so what's the guarantee for the FedLin? As you might guess, if FIs are smooth and strongly convex, FedLin achieves linear exponentially fast convergence rates. this factor kappa, as you see here, might seem familiar to you. This is the usual linear rate that we get for strongly convex functions in the central setting. So in other words, FedLin is matching exactly the same rate of the centralized gradient descent up to a constant difference in terms of the convergence rate. And what's also important is that we can show that this bound is tight for FedLin, meaning that we can provide lower bounds. So we can provide settings for which FedLin exactly has this speed that you see in the theorem. Okay, so we also have lower bounds, and this speed is actually tight for FedLin. And also another important takeaway here is that the convergence rate is independent of how fast or slow are these machines. So somehow FedLin is also robust to stragglers in that sense. We can provide a similar guarantees. Actually, specifically, we can also get the same rates as the centralized gradient descent for cases when the problem is convex and not strongly convex, and for also the case when the problem is non-convex. And finally, let me just say one or two words about the sparsification. So what we use is the top K sparsification idea to basically compress the messages that are exchanged between the server as well as the clients. And of course, in order to make it precise, we have to use some other ideas. So we have to basically consider error feedback and so on. And FedLin can be considered as one of the first works that basically studies the effect of these type of sparsification techniques in federated learning when we have objective and systems of heterogeneity. Of course, we can also use other sparsification techniques like quantization methods that Dan is an expert of, but that's left for future work here. All right, so this brings me to the end of the first part. Let me quickly mention an important open problem here. So right now for FedLin, we have assumed arbitrarily heterogeneity, right? We have assumed that the functions fi could be anything, and also the clients could take different steps. Now, this arbitrary heterogeneity may not be something that happens in practice for federated learning. I mean, we studied the problem from the optimization perspective, but in practice, the local objectives in federated learning, they have some shared structure, right? I mean, if you, for example, distribute the CIFAR data set or the MNIST data set among the clients, I mean, these specific chunks of the data set, they are related to each other. It's not that they are completely different objectives and different loss functions. Now, the question here is that how can we exploit this objective, this similarity, or how can we add some similarity assumptions between the local functions in order to exploit the effect of, for example, fast nodes? So right now in FedLin, we have to penalize those fast nodes because we are assuming arbitrary heterogeneity. But if there is some similarity across the local objective functions, there might be something more that we can say. All right, so that brings me to the end of the first part. For the remaining, I think I have like maybe 5 minutes or maybe less. I just want to quickly review some of the highlights.
Sorry, Hamid.
Yes.
Yeah, just so you have more than like 15 minutes. If you like, we can take the questions throughout it. So yeah. So overall, like.
Okay, so I will. Okay, good. I will try to basically wrap up quickly and mention only the highlights of the second part. Thank you.
And may I have one question?
Yes,
there is also a question from audience. So my question would be like for your theoretical result for FedLin, it seems to me that like you cannot really show that, for instance, or maybe correct me if I'm wrong. So if, for instance, if those fast nodes, if they would run the same number of steps as the slowest nodes, but you don't decrease the step size, you just use the same step size, I suspect you would get exactly the same result, same convergence result, and you cannot really show that the actual results running more steps on those faster devices leads to better convergence. Is this correct?
Yes. Okay. So let me see if I understand you correctly. So you're saying that if you use let's assume that, are you assuming that we use the same learning rate for all the clients? Why they have different local rounds? Is this what your question was? So the same learning rate or the same number of local rounds?
No, yeah, so like right now you have a setup, right? That the fastest devices they run more local steps.
More local rounds, right?
But you have to penalize the step size.
Right, exactly.
So you have to decrease the step size. So my question is that if you don't penalize the step size, you use the same step size for every single device, but you only run the number of rounds that corresponds to the slowest device, whether you would obtain exactly the same convergence result, or you benefit from running them.
Yes, we will. So so what you are saying is this: run the same number of local rounds. Okay, so fix the same number of local rounds to H, but clients could have different things, and eta would be the same. So you can show that if eta behaves like 1 over H, the number of local rounds to the fixed number of local rounds, then you get exactly a similar result, similar convergence result. You are right.
Yeah. So that means like because you have this like arbitrary heterogeneity, you cannot really show that you get an improvement on running more local steps on those faster devices.
You don't get, right? Exactly, because FIs are very different from each other, right? What I mean, if you have total heterogeneity, right? If you don't assume anything about the connection of FIs, there's not much more that's my opinion, of course. There's not much more that you can do. You cannot see the benefit even of local rounds.
Yeah, thank you. So there are like two or right now even 3 questions from the audience. So I'll try to unmute Edwin. He has the first question.
Yes, hey, can you hear me?
Yes, thank you, Edwin.
Yeah, so I have 2 questions. So the first one is that, do you update the learning rates during the training, or are you assuming that the speed of the clients is known?
Very good. So our algorithm as well as FedNova assumes that tau i's are known and are fixed.
Okay.
Right. So you basically fix the learning rate. You can consider settings where the learning rates would be, so the tau i's would be different across rounds. I suspect that if you still normalize the learning rate in this way, according to the specific tau I that you get in each round, you would still guarantee convergence. So I mean, thinking about our analysis, I think everything goes through.
Okay, thank you. And the other question was that have you done any analysis on what different batch sizes would affect the learning instead of different learning rates?
Very good question. So that's excellent question. So right now, at least for the FedLin part, we assume that the local, you can compute the gradient of the local functions Fi, right? But another way to do, another approach to systems heterogeneity would be the following. We would be assuming that the local nodes do a stochastic gradient descent. But for example, if you are given a fixed deadline, we would basically play with the batch size, mini batch size, to basically meet a deadline, right? So there would be again a trade-off here with the size of the mini batch as well as the number of local rounds and so on, and the speed that the client has. To the best of my knowledge, I don't think this has been studied before. That's a very good question. Here we assume that gradient of FIs are given. Yes.
So there is another question from Bo. So I'll try to unmute Bo.
Oh, hi. Can you hear?
Hi, Bo.
Hi.
Yes.
Thanks a lot. I just have 2 questions. So first, can you elaborate a bit more on slower client is more valuable? Like, what does it actually mean by the slower? Does it indicate more training samples or taking more steps for converging?
All right, very good. So right now, by a slow client, so think of it from the computational aspect. A slow client could be, for example, let's say a smart watch, an Apple Watch, for example, right? I don't care how many data points it has. I don't actually know. What I care is that the time that it takes for this slow client to do one local round is considerably more than the time that it would, for example, take for an iPhone to do one local round on their data. Okay, whatever data they have, right? Yeah. What's important for me is to measure the time that it takes for the device to do H local rounds. Okay, whatever data it has, I don't care about the data. What's important for me is how many seconds does it take for it to do, let's say, 10 local rounds compared to an iPhone, for example.
Yeah.
Okay. Yeah, that's the definition. So we don't care about the number of local data points. Of course, that's important also, but what we really care about the time that it takes to do one local round, right? One gradient update, for example.
Yeah. Yeah, right. Yes. Okay. And also, like you mentioned, the local objective function is different from the global objective function, but I'm a little bit confused. Does this different mean the formulation is different, or does it mean the local convergence point is different than the global one?
Both. So so when you consider a general notion of objective heterogeneity, you can think of it like this. Client, so consider two clients. One client has, so each of the clients has some data sets, local data set, but these data sets are, let's say, they are generated from different distributions. They might even contain different data points, like data points that look differently. So one is, let's say, whatever. If it's language data, one is with one accent, the other is with another accent, for example, right?
Yeah.
So these are heterogeneous. So their local functions, FIs, are different, right? They don't look like each other. And also, these FIs are different from the average function, the global function, the sum of the two. And even their minimizer should be different, right? A model that would work for both is not the best model that would work for one, right? So here we are considering a very general notion of objective heterogeneity. The minimizers are different, the structures are different, everything is
different. So does that indicate that we are doing different tasks on different devices, or?
Well, right now we are looking at it from the optimization perspective.
Yeah.
That could be the case, actually. Okay. So right now we are abstractly looking at it as minimizing an objective function, a mathematically defined function f or fi, right? Oh, yeah, but it could potentially correspond to different tasks too.
Okay. Okay, great. Thanks a lot.
Thank you. All right. Are there any other questions, or I can maybe continue for a few minutes?
Please continue. Yeah, please continue. Okay. Like we have still like eight minutes. Maybe we can go a bit over time if people are like willing to stay. But normally
that's fine. Okay. All right. Let me see if it works. All right, good. So the second part will be about adaptive selection approaches. And as I said, I will just quickly mention the main highlights. I don't want to take your time a lot. So remember, adaptive selection approaches, as you see on the right-hand side here, here at each round, we would adaptively select a subset of the clients that would participate in the training procedure. And this selection is an adaptive procedure. But what's important is that we will wait for all those selected clients to finish their local rounds. All right. So what's the main idea behind these adaptive selection procedures? In these adaptive selection procedures, of course, we want to exploit the speed of fast devices. We are hoping that those fast devices would help us in converging faster as compared to the slow devices. Okay, so in this sense, we somehow need to relax this assumption of full objective heterogeneity. I mean, we cannot really assume that all those devices have very different objective functions, because then using fast devices would be meaningless, would be hopeless for us. Okay, so in the second part, we are assuming that these functions have some degree of homogeneity, meaning that they might be somehow similar in the sense that if you use fast devices, if you minimize the objective function for fast devices, it has something to say about the global minimizer too. Okay, so just for simplicity, in the second part, I want to relax this assumption on objective heterogeneity, and I'll focus on addressing the system's heterogeneity challenge by using these adaptive approaches. So a small change of notation here, just to make it compatible with the paper. So here, instead of fi that I was using in the first part, I would use li, L standing for the loss function, and instead of the variable, the model that I was basically using as x, here I would use w for the model that I want to train. But the rest is the same. The clients have local data sets, they have local loss functions, empirical losses. And here, just for simplicity, you can assume that the data distribution of the clients are homogeneous, meaning that they have instant realizations of a common data distribution. Okay, so that's our setting, and we want to address the challenge of systems heterogeneity. Okay, so here, again, let me remind you, we have n heterogeneous devices. Some of them are fast, some of them are slow. For the sake of, for simplicity, assume that the devices are ordered from the fastest to the slowest. So the first one, device number 1 is the fastest one, device number n is the slowest one. Okay, oh, sorry, I don't know what happened. All right, so we were here. So heterogeneous devices, fast and slow. Now, here we're going to introduce an algorithm which is called FLAMP. Let me explain to you the high-level picture of how FLAMP is operating. So the basic idea is the following. Remember, it's an adaptive selection procedure. In the beginning, we start with a very small subset of the clients, which correspond to the fastest clients. Okay, so as you see here, you pick N0 fastest nodes, and you would only train a model using those fastest nodes. Okay, so for example, in practice, you would pick 3 fastest nodes inside all your clients, and you would only train using those fast nodes. Okay, of course, those fast nodes have a limited amount of data. Right? If each of them has, let's say, 100 data points, three nodes would be 300 data points. That's not a lot, right? So there's no point in training a model using these fast nodes for a long time because they have a limited number of data points. So essentially what we do here is that we would train until we are sure that we have somehow trained enough such that the effect of all the data points have been considered. So more formally, we would train for these fastest nodes until some statistical accuracy is achieved. Okay, I will elaborate more on this in the next slide. Okay, what's important here is that since we have a limited number of data points, we don't train forever. Okay, we train for a small amount of time just to make sure that we have reached a good model, considering the fact that we have a small number of data points corresponding to these fastest nodes. Once we reach this statistical accuracy, it's time to add more data points. Okay, so it's time to add more clients to our set of training clients. So what we do is that we double the number of clients inside our selection set. Okay, and we will again continue training, but we continue training exactly from the model that was trained at the previous batch, right? So once we double the number of clients, our initial point would be the model that was trained at the previous batch using the N0 fastest nodes. Again, we train now using twice number of nodes. Some of these nodes are slower than the previous batch, but it's fine. We are using their data. And again, we train in a sense that we would reach some level of a statistical accuracy. Once we reach that statistical accuracy, the same procedure is repeated. We double again the number of users, and we continue this procedure until the end, until we basically have included all the devices, no matter how fast and slow they are, inside our training procedure. So that's our adaptive selection scheme in a nutshell. So the meta algorithm would be the following. As I mentioned before, you start with a small number of fast nodes, and you train. Okay, now the training is done using our off-the-shelf or our favorite federated solver. That part, any federated solver could be basically be integrated in this meta algorithm that I mentioned. So you train until you reach some statistical accuracy, then you double the size to add more data points. Again, you train using until you reach the statistical accuracy of the new set, then you double and you continue this procedure until you use all the devices, the data of all the devices. Now, okay, I mean, I explained this before. Why do we train until we reach the statistical accuracy? Because there is really no point in, if you have, let's say, if you are training using three faster devices, there is really no point on training forever, because at some point, since we have your limited amount of data, at some point you reach the best test error that you could have reached, right? The best statistical accuracy. So there's no point to train further. Okay, so you have to stop there and go to the next round, because you want to save in terms of the time that you are also using for training, in terms of the wall clock time. That's really the core idea here. Now, another point is that as the federated solver that you use for the inner loop of training, you can use any method, any off-the-shelf method, Fed average, scaffold, Fed prox, Fed gate, and so on. So what we will do, what I will explain is to use FedGate as the local solver. Okay, FedGate is one of the recent algorithms that have been proposed. It's quite fast and good compared to like the counterparts such as scaffold and so on. It also considers heterogeneity among the objective functions and also adaptable to quantization. So it's a good algorithm to use here. Okay, again, using FedGate, the training procedure would be the following, a typical training procedure. You start, for example, in the beginning, you start with the three fastest nodes. For those three fastest nodes, you run FedGate, your federated algorithm. You run FedGate until you reach the statistical accuracy. Then you add more participants, double the number of participants. So then you consider the six fastest participants. You again run FedGate until you reach the statistical accuracy. Again, you double, you continue this procedure until you basically involve all the nodes inside your training procedure at the end. And as I mentioned, FedGate would be a good option because it handles all these challenges that we have been considering so far in federated learning. And what we can show is that by integrating FedGate inside the meta algorithm of FLAMP, you can basically provably show a speed up in the system, in the case of system heterogeneity. All right, so let me, for the sake of time, quickly just don't go through these theoretical arguments. You can basically specify the number of rounds that you need and everything like that using the statistical accuracy. What's important in the end, the final theorem that you see at the bottom of the page, that's really important, is that we see tangible speedups. So if you look, remember, the local solver that we are considering is FedGate, some state-of-the-art method in federated learning. You can consider whatever, scaffold or something else, that doesn't matter. But the expected time that it takes for the algorithm FLAMP to get to a good solution compared to divided by the expected time that it takes for the local solver to get to a good solution, the ratio is of order 1 over log of the total number of data points in the system. So if you are training, if the total number of data points is 50,000 data points, then FLAMP in expectation would take, let's say, a factor 15 less time to reach to a good solution. And time is basically the wall clock time, the amount of time, total time that it takes to converge. So that's the theoretical result. Also, experimental results show that this algorithm is actually performing very well. So for example, if you look at the plot on the top right, and you have to compare the wall clock time. So this would be the most right plot. In terms of wall clock time, you see that FLAMP is quite superior with respect to FedNova, which is one of the state-of-the-art methods in this context. And also with this usual idea of partial participating nodes, also FLAMP is performing well in terms of the final statistical accuracy that we are reaching. Okay, let me actually stop here. Thank you very much, and sorry that it took a bit over time.
Well, thank you for the talk. I'm wondering if there's any other questions. I couldn't see any on the list. Is there anyone with their hand raised? I will just maybe add one last question, and
sure.
Then we can wrap up.
Sure.
It seemed to me like for FLAMP, you need the number of local steps to be like this H to be constant. Like what happens if this varies?
No, it's like this. So in adaptive selection procedures, you at every round you pick a subset of the clients.
And they take each step. Yeah.
They take each step, and you wait for the slowest to finish. So they have different computation times, but you wait for the slowest. Now your question is, so here we are basically telling the clients to do this number of local steps, and we are willing to wait for them to finish. So that's the adaptive selection.
I understand, but I was wondering if there's some let's say some you could have this number. I mean, is it important that all of them take exactly 8 steps, or can there be some noise with respect to the number of local steps?
Yeah, that's a very good question. Actually, right. I think as long as in the homogeneous setting, you need a minimum number of local steps.
Right. That's what
the rest is fine. Yeah. The rest is fine. Yeah, that's a very good question.
So basically, like you could wait for the slowest one in some sense to take H, but then the faster you could actually take advantage of additional steps.
Right.
Yeah, that was basically my question. All right. So I think since we already had quite a few questions earlier, I think I'll thank Hamid a lot for the very interesting talk.
Thank you very much.
And yeah, it was a pleasure to host you. And thanks everyone.
Thank you, Dan. Thanks everyone.